Sure, I can do a quick introduction. So it's our pleasure to welcome everyone to the first NPI webinar of the fall 2019 semester. We'll be doing these periodically throughout the academic year, highlighting recent research results from NPI faculty and students. Today's presentation will be by Mina Arashloo from now Cornell. Until recently, she was a PhD student at Princeton. And she's going to talk about some work that's going to be published at NSDI next spring. So take it away.
Well, thanks, Nate. So today I'm going to be talking about Tonic, which is a programmable hardware architecture for implementing transport protocols on high-speed NICs. And this is a work that, as Nate mentioned, was something I did as part of my PhD at Princeton, and it's going to appear in NSDI 2020. So since the beginning of networking, there's been constant innovation in the type of algorithms that run in the transport layer, both for doing congestion control and reliable data delivery. And the reason that there's been this much innovation in the transport layer is that the algorithms in this layer can be really customized to the specific network, to the specific needs of network operators, the network topology, the workloads that they're running, the performance requirements of the applications that are using the network in terms of latency, throughput, if they have deadlines or not. So it has always been really important for operators to be able to basically tweak the algorithms in the transport layer to actually fit it to their specific needs. And this hasn't really been a problem until recently because the transport layer is part of the network stack, and it has typically been implemented in software, either in kernel or more recently in user space, which means people can just go and find the part of the transport layer they want to change and make their desired modifications to it. But the problem is, as servers in data centers are moving to higher speeds from 10 Gbps to 40 Gbps, and now more recently to 100 Gbps, the CPU overhead of running the network stack in software is actually becoming really prohibitive. And there's been measurements in large cloud providers like Google and Microsoft that shows that for applications that use the distributed applications that use networks a lot for communication, about 30 to 40% of their processing cycles can actually be wasted on doing networking. And this is starting to become more prohibitive as the link speed is going up. So there's been this trend with several companies that they're starting to implement fixed function hardware network stacks that can run entirely on the NIC. So they wouldn't consume any CPU overhead, any CPU cycles, but they're fixed functions. So the algorithms in a transport layer and the other layers of the network stack are basically fixed. And the operators have to live with whatever algorithm the vendors of these network stacks decided to basically implement. So our goal in this project was to bring the best of both worlds together, which is we wanted to create this hardware architecture for the transport layer that is programmable, so people can basically make modifications to the behavior of the transport layer with modest development effort, but can also run as part of a hardware network stack so that people can benefit from the low to no CPU overhead of these stacks that run entirely on the NIC. So a natural question that comes up here is that we've been seeing the emergence of these smart NICs that have FPGAs embedded in them, which are fully programmable. So why can't just people go and program these FPGAs and basically implement whatever transport functionality that they want on these FPGAs themselves? And the simple answer to that is that it's basically very challenging to implement the transport layer on a high-speed NIC. And this is mainly because of the two constraints that I'm just going to tell you about. The first one is timing constraints. So measurements have shown that median packet size in data centers is around 200 bytes. And if you want to support small packets like 200 bytes or let's say 128 byte packets at 100 Gbps, you have to be sending a packet out every, let's say, 10 nanoseconds. And there's very standard hardware tricks that you can use to keep up with this throughput, but also buy yourself more time to process each packet. You can create a processing pipeline in which each stage basically sustains the 100 Gbps throughput. So you're sure that you can send a packet out every 10 nanoseconds, but you have the length of the pipeline, so more time to process each packet. But what makes it a little bit more challenging to do that here is that, as I'm going to show through examples throughout the talk, is that the kind of processing that happens in the transport layer is kind of back-to-back stateful event processing. So basically, you are keeping some state for each flow in terms across its packets. And as different transport events come in, you want to change that state and basically ensuring that state remains consistent at that high speed across a large pipeline is not a trivial thing to do. And the second set of constraints are memory constraints. So the commodity NICs today only have a few megabytes of high-speed memory on the NIC. And in a typical data center server, you can have more than a few thousand active flows at a time. So that leaves you only with a few kilobits of state for each flow. And given that at high speed, these flows can have a lot of data in flight, this doesn't leave you with that much state to work with. So what Tonic does is that it provides this programmable hardware architecture that can satisfy both of these constraints. So it can basically run within a network stack that can sustain 100 Gbps, so it doesn't become a bottleneck. And it can also kind of run within the memory limits of commodity NICs, so only a few kilobits of memory per flow. And it also allows people to basically change the behavior of the transport layer with modest development effort. So to do that, our main observation was that there are a lot of common patterns across different transport protocols in how they pick which packets to send out next and at one time. And it's possible to basically extract those patterns and implement them as very efficient fixed function hardware modules that can be reused across different protocols. So basically it can help us create this efficient hardware template for the logic of the transport layer, which is basically where you need programmability for all of these algorithms. And this serves two purposes. One of them is that it reduces the functionality that users must specify. And it also allows us to basically take all of these reusable components and implement them very efficiently to meet both of the constraints that I just described. So before going into more detail, I just want to give an overview of, when we say, Tonic is going to run as part of a hardware network stack, where we're actually assuming each part of the network stack is, and where the applications or where the memory is. So we're assuming that the applications are running on a host and their data lives on the memory that is on the host. And because we're talking about a hardware network stack, we are assuming that the IP layer and Ethernet layer and below, they're sitting on a NIC. So the transport layer, the main part that consumes a lot of CPU, which is the data transfer, we assume that it is on the NIC. But we do assume that there is a shim layer, a small part of the transport layer on the host that performs functionality that doesn't need, low latency or high throughput, like connection management. So basically tracking the TCP state machine to see if a connection is starting or a connection is ending. And also to relay application requests for data transmission. So basically, if a new connection starts or a connection ends, that shim layer can tell the NIC to add that connection or remove that connection. And also when the application asks to send some bytes from, let's say, memory address A, then that shim layer can basically relay that request to the data transfer part of the transport that is sitting on the NIC. And for this module, there's basically this part that is supposed to decide, for doing the data transfer, that is supposed to make most of the decisions that transport algorithms make, which is which set of bytes go into the next packet and when that packet is supposed to go out. And that is the part that is a focus of Tonic, which is the part that we're trying to make programmable to allow people to basically experiment with different algorithms. And once you decide which set of bytes are going to be going out, then you can ask a DMA engine to actually fetch those data segments from memory and send them to the IP layer and below to actually create the packets and send them out. So the disclaimer here is that the transport logic part that we're talking about doesn't really need to deal with data, because it can basically use metadata, the segment addresses and everything, to decide when you need to send a set of bytes out, and then it relies on the DMA engine to fetch that data from memory and send a packet out. And the second disclaimer is that all of the discussion today is going to, which is the focus of Tonic, is going to be on the sender side of the transport layer, except, apart from the more recently receiver-driven protocols that have been introduced, most of the logic, like the more complicated logic of the transport layer, happens on the sender side, and that's why that is a focus of Tonic. And as I'm going to mention later, implementing a programmable receiver is something that we're considering as part of our future work. All right, so now to just to warm up, I want to go over very quickly a review of how TCP works that I assume everybody is kind of comfortable with, but just for warm up. So TCP is the most common transport protocol. It's the most commonly deployed protocol out there. And what it does is that when an application on a sender let's say wants to send data to another application, to the application on another end host, it will ask the transport layer to do so. And what TCP, which is implemented in the transport layer, does is that it performs reliable data delivery and congestion control. So it makes sure that all the bytes in the data are received at the receiver, and also they're transmitted at a pace that doesn't overwhelm the network. How does TCP do that? It keeps some state per flow, which is typically the status of every byte. Basically, if that byte has been sent out, if it has been delivered or not, if the TCP thinks it's lost, or if it's been retransmitted. And also to control how fast the data is going out, it will only send out a window worth of bytes at a time, and doesn't send out more unless it's sure that some of them are at least delivered. So now let's see an example. And for the simplicity, for the sake of example, I'm assuming that every packet is only carrying 1 byte, and the window size is 5. So when TCP starts for that flow, it will send 5 packets containing the first 5 bytes in the window to the receiver, and mark them as being in flight. So here it's marked with color yellow. Then let's say all of them are received at the receiver. The receiver is going to send some X back to the sender. So the sender can mark all of those packets as being basically received, successfully delivered to the destination, and move the window forward. And it can send another 5 packets out for bytes number 6 to 10. And let's assume that packet number 6, which contains byte number 6, is now dropped. So the sender is not going to be receiving an ACK for that packet. And based on that and other signals from the receiver, it can basically conclude that that packet was lost, most probably, and retransmit that. So this is how it can, TCP can ensure reliable data delivery. And it can also reduce the size of the window, because a packet loss means that probably there was congestion in the network. So you want to slow down on how fast you're sending packets out. So the main thing that I wanted to basically emphasize here is that kind of stateful event processing that I was talking about earlier, which is you keep some state in the transport layer in TCP and other kind of transport protocols. You basically keep some state across different flows, and when different events happen, if you're transmitting segments for that flow or acts or timeouts happen, you basically modify that state. So there's stateful event processing happening here. So just to generalize a little bit, because we want Tonic to be able to support a range of transport protocols and not only TCP, this is how the network stack is generally going to look like. Applications are sitting on a network stack. They ask it to transmit data for them. The transport layer is sitting right afterwards. It is keeping some state per flow, which is very similar to TCP, the example that we just saw. There is like the status of every byte, and also some notion of credit to basically control how many bytes the flow can send out at any time. And in the case of TCP, that was kind of controlled by the window. And then the transport layer will basically tell the other layers of the network stack which flow should send what data segment out after next. So the two main things, as I've mentioned multiple times so far, that the transport layer needs to do, and this is the terminology that I'll be using throughout the talk, is first credit management, which is how many bytes each flow can send out at any point in time. And the second one is segment selection. So basically, given that I can send out n bytes at this moment, which set of bytes are going to be out in the next packet? Is it going to be new set of bytes that I haven't sent so far, or is it going to be bytes that I had sent before and I think they're lost? So kind of parallel to these two main functions that a transport layer has to perform, Tonic also has 2 engines: a segment selection engine that makes decisions about the contents of the next segment for each flow, and a credit management engine which decides when that segment will be sent out. So the segment selection engine is going to keep track of the active flows, the flows that have data to send out at that point in time, and generate segment IDs for them and send them to the credit management engine. And the credit management engine will keep a separate queue for each flow and queue up these segment IDs. And based on the amount of credit that each flow has, we'll send them out. So what I'm going to do now is that I'm going to go into the patterns that we found in segment selection and in credit management, and how these patterns helped us create and design each of these modules in Tonic. So segment selection. Segment selection is also, typically called reliable data delivery. And at a high level, it actually works in a in a pretty simple way. You basically keep some state for every byte and update that as different events happen, like as you kind of generate more segments or you receive acts or timeouts. And based on that information, you basically pick which set of bytes should go out in the next data segment. And the problem here is that just because of the sheer amount of like amount of bytes that each flow can have in flight at any point in time, we cannot maintain per byte state for every flow on the NIC because of that memory constraint that I was talking about earlier. So what we do, which is something that many TCP implementations do as well, is that in that shim layer for the transport layer that is sitting on the host, before we relay the application request for sending data to the NIC, we basically partition the data into same side segments. So we pre-calculate the segment boundaries and then just tell Tonic how many segments it has to send out and the starting address. So Tonic will basically be able to keep per segment state instead of per byte state and just select the next segment based on that. So now let's see the patterns that we found in each of these things that happen in segment selection. So first I'm going to talk about the patterns we found for the state that protocols keep for doing reliable data delivery and how they update them. First, what we observed is that actually most protocols just use a few common bits of state per segment. So they basically keep track of whether the segment was ACKed, whether it was retransmitted, or whether it was lost. And this is just, I mean, they can keep some other information, but this is, I'm just focusing on per segment information here. And this is, so these 3 bits are usually enough for most protocols to kind of basically make deductions about everything else. And the kind of updates that happen to all of these bits except for lost, the one that is keeping track of whether that segment is lost or not, is actually similar across most of these protocols, because these protocols keep this per segment information for a window of segments. So the implementation of that would be maybe using a bitmap. So you use a bitmap to keep track of this information. And the update, usually when an ACK happens or something, this window will be moving forward. And or when selective ACKs come in, these bitmaps are updated to basically represent which of the segments were ACKed using those selective acknowledgements. So basically, this set of updates is common across all protocols, and we can just implement them as fixed function modules in Tonic. And that is actually very useful for us because these operations, although they sound very common, doing them in hardware using bitmaps is not straightforward, and it can have some overhead. So we can basically implement them in an optimized way so that it fits our memory constraints and timing constraints, and Tonic users won't need to actually worry about that. So the only thing that these protocols do differently is that based on the other bits, so the other pieces of information like ACKed or retransmitted or other pieces of information, is how they decide whether a segment is lost or not. And that is basically what differentiates these algorithms for segment selection from each other. So some algorithms use, triple duplicate ACK like TCP. There are other algorithms that use selective ACKs in very clever ways to decide whether some other segments are lost or not. So this is the part that Tonic needs to provide some programmable modules for users to basically specify their logic for detecting lost segments. But even there are still patterns. So usually to detect whether a segment is lost or not, the sender relies on 2 types of information: either external information like ACKs that come in incoming packets, or the absence of this information for some specific amount of time, which is timeouts. So Tonic only needs to provide 2 programmable modules: one for the for the programmer to specify how to specify how they want to detect lost in response to ACKs, and the other one to specify how they want to detect lost segments in response to timeouts. And the other nice byproduct here is that these 2 signals are mutually exclusive. So you only receive a timeout if you haven't received an ACK for a specified amount of time. So that means that these 2 modules are not going to be updating the state of the same flow at the same time. And it makes our design simpler. So now moving on to, so this is all the patterns we found for the state that these protocols keep per segment and how they update them. So given this information, they have to select the next segment. But what we find out is that almost all protocols, if they have some segment that they think is lost, they prefer to retransmit that first before sending anything new. And the reason is that the receiving side in most applications typically processes data in order. So it doesn't make sense, if you already think that a segment is lost, it makes more sense to actually transmit that first instead of sending anything new. So this is again another module that we can implement in a fixed function manner in Tonic and just relieve the programmers from actually doing it themselves. So now let's see how Tonic's segment selection engine works. So Tonic's segment selection engine has a memory that keeps per flow state. So these bitmaps that I talked about, which keep track of the status of every segment, the size of the window, and other relevant information. And then there are multiple events that can happen that can basically trigger that update to the state for each flow. So for example, one of these events is if there is an active flow. So basically, the Tonic keeps track of the set of active flows, which are the flows that have some data to send at that point in time. And if that set is not empty, it will generate an event that will trigger segment generation. And as I described in the previous slide, this module can be implemented as a fixed function module, because it can just fetch the flows state from memory, look at the segment status. If there's anything marked as lost, it can basically generate the segment ID for that, the segment address for that, and if not, generate a new address of a new segment. Another event that can happen is the receipt of an ACK, or like other similar incoming packets. So those events are processed by a two-stage pipeline. The first stage of that pipeline performs those common updates that I just described, moving the window forward, updating all the bitmaps, except for the one that is keeping track of lost segments. And that last bitmap is going to be updated in the second stage of that pipeline, which I've marked as red because it's a programmable module. So in that stage, programmers can basically use all the updated information from the previous stage and also the per flow state to basically decide if any segment is lost and mark it in the bitmap that keeps track of that information. Another event that can happen is a timeout. So the way Tonic keeps track of timeouts is that it basically goes through all the active flows one at a time and basically checks if the timeout has expired or not. And this is usually okay because timeouts, like Tonic's clock cycle is 10 nanoseconds, and timeouts are usually on microseconds or milliseconds timescales. And basically, if a timeout has happened, again, in another programmable module, the user can specify how they want to basically perform loss detection and recovery, if they want to mark some segments as lost, and if they want to change any other parameters like window size or other parameters. And what I want to, another thing I want to emphasize here is that all of these basically processing modules, event processing modules, they all need to read the state of the flow and basically process it and modify it in some way. And because we wanted to basically process these events the moment we got them, we basically wanted to allow concurrent access to this memory, to all of these events, to all of these processing modules. So we built a memory that has multiple read-write ports, which is something that has non-trivial overhead. So that's another thing that the users don't need to worry about. Also, it could be the case that two of these modules actually modify the state of the same flow. So let's say you're generating segment IDs for a flow while you're also receiving acknowledgements for previous segments that you sent out for that flow. But given all the patterns that we talked about before, we have managed to basically create a fixed function marriage module that can consolidate the state if something like that happened, if concurrent updates happen, and consolidate before writing the state back to memory. And there are also other other events that can basically happen here, but that I've excluded for simplicity. But what I want to emphasize here is that the only thing out of this whole picture, the only thing that Tonic's users have to specify is basically the logic that goes into those two red boxes, and then the rest of the segment selection engine is going to take care of everything else. So with that, let's move to the patterns that we found in the way different protocols perform credit management. So if you look across the literature of congestion control, credit management is also commonly called congestion control. There are two main ways for protocols to perform congestion control or credit management. The first one is rate control, which is where the sender basically receives some signals from the network or the receiver and basically paces how fast packets are going out for each flow. And this is usually done either using a window or setting the actual data rate, with rate being a little bit of an overloaded word here. So let's look at how this is usually done. So usually these protocols have, and there's like other common schemes, but I'm just going to go through rate control first. So it's usually a control loop, and it continuously monitors the network to estimate the available network capacity, and then adjust some parameters, which are the window size or rate. And then these parameters, the window size or rate, can be used to calculate exactly at any point in time how many bytes of credit that flow has, as in how many bytes it can send out at that point in time. And what we realize is that usually, I mean, most of the programmability in these protocols comes in the way they adjust the parameters based on what they monitor from the network. And what we realize is that there's a pattern there. There are two main signals, again, for deciding parameter adjustment and for deciding how to adjust these parameters. The first one is a set of external signals, so like ACKs or condition notification packets, something that comes from either the network again or from the receiver, or it could be periodic internal signals like counters or again some other types of timers. And as you can see, this actually aligns really well with the existing programmable modules that we had in the segment selection engine that were doing loss detection and recovery. So what we do is that we allow basically to basically reduce the development effort and have all the programmable modules in one place. We basically allow programmers to also keep these parameters in the segment selection engine and update them in those two programmable modules, and then send the updated parameters to the credit management engine so that it can basically enforce them and calculate the credit based on them. So that's for rate control. And the second category of protocols basically use admission control to do congestion control, which means, which is actually pretty simple on the sender side, which means that the receiver or the network is going to tell the sender when it can actually send anything out using tokens. So the sender can only send something out for a flow if it has received a token for it. So the logic here is actually pretty simple. The sender just needs to keep track of the total amount of tokens that it has for each flow. So now let's take a look at how Tonic's credit management engine actually looks like. So again, similar to this segment selection engine, it has a memory that keeps some per flow state. The per flow state here is basically a separate queue for each flow that it basically keeps all the segment IDs that were generated by the segment selection engine for that flow but haven't been sent out yet. The amount of credit in terms of bytes that flow can send out at that point in time, and some other variables like the most updated rate or congestion window and other things, or the number of tokens. And the two common basically events that can happen in all these different categories of credit management that I talked about. One of them is actually this is actually reversed. So when there is a flow with enough credit, let me actually put both of them here. So the events are actually reversed. When the credit management engine receives a flow ID and a segment ID from the segment selection engine, it will in-queue it into those per flow queues. And it also keeps track of the flows that have enough credit, and then every cycle it just takes one of them, transmit a segment ID from the head of the queue, and reduce the amount of credit that flow has. And again, similar to the segment selection engine, these modules read concurrently from the memory, and there are also other modules that can be here for let's say tokens, like for different credit management engines, like to basically change the other variables. And again, similar to the segment selection engine, there's a merge module that basically consolidates the state if two of these processing modules happen to update the state of the same flow before writing it back to memory. So as you might have noticed, there's actually no red box here. So everything here is fixed function. And the reason is is that most of the programmability was actually pushed in parameter adjustment, and everything was pushed to the segment selection engine. So in terms of credit management engine, it basically just queues up the packets and keeps track of the credit and enforces that. So we have three types of credit management engine, one for doing rate control with congestion window, one for doing rate control with data rates, and one for admission control. And the users of Tonic can just pick among one of those three. So now that we have enough details about how Tonic actually works, I want to briefly talk about what was difficult to implement in hardware in Tonic, because that was kind of one of the main things, one of the main reasons we started this work, because we wanted to take those challenges away from Tonic's users. The first one was consistent stateful operations. So as I've mentioned multiple times throughout the talk, and as you've seen, different events that happen in the transport layer will update the state of the same flow. They can update the state of the same flow. And the path we decided to take to basically make sure that we can process these events as fast as possible and also keep the state consistent at any point in time was to create this kind of big multi-ported memories that, you know, all of these processing modules can read and write, read from and write to at the same time, and also that merge module that could reconsolidate the state. And specifically creating that big multi-ported memory was a huge push both on the memory constraints and the timing constraints. And that is something that we managed to implement very efficiently in Tonic. So Tonic's users don't need to even think about whether, you know, the changes they're making to the state variables in different modules is going to stay consistent or not. The second one was bitmap operations, as I mentioned before. So especially in the segment selection engine, you know, you're keeping track of these bitmaps that keep track of the status of every segment, and just implementing different things like sliding window over these bitmaps is actually pretty challenging to do efficiently, and that is something that Tonic can take care of without the users worrying about that. And the other one was per flow rate limiting. So for protocols that use rate control with data rate for for credit management, we needed to do per flow rate limiting for about a few thousand flows, about 2,000 flows, and because we wanted to finish you know, our processing within 10 nanoseconds, we didn't want to do any floating point operations to basically calculate based on the rate how many bytes the flow can send out at a time. So we had to do some, you know, approximations using and optimizations using integer operations instead. And there are more details about all of this and also Tonic's architecture in the paper, which I'll encourage you to look at if you're interested. So to evaluate Tonic, we basically evaluated it in 3 different dimensions. The first one was programmability. So we wanted to make sure that Tonic can allow people to implement a wide range of transport protocols. So we implemented 6 protocols that we believe are representative of a variety of protocols. The first one are Reno and New Reno, which are representative of TCP variants that use cumulative acknowledgement for doing loss detection and recovery. The second one is SAC, which is kind of a TCP variant that we implemented based on RFC that uses selective acknowledgements for doing loss detection and recovery. The third one is NDP, which is a recently proposed receiver-driven data center transport. And because it's receiver-driven, well, disclaimer, the sender side is actually pretty simple. And the other 2 are DCQCN and IRN, which is basically used in the RDMA context. And all of these protocols, when implemented in Tonic, they meet our timing for 100 Gbps for 128 byte packets, which is a 10 nanosecond clock cycle. And what I want to emphasize here is that all of these were implemented within 200 lines of Verilog code in those programmable modules, and use a little bit of the very tiny bit of the logical resources. And comparing that with the reusable modules that we implemented, which is around 8,000 lines of Verilog code, we believe that is a considerable reduction in development effort on the programmer's side. The second dimension for evaluation was scalability. We wanted to know how scalable our hardware architecture is, and we experimented with multiple variables. One of them was the complexity of the user-defined part of Tonic, which were those red boxes that I showed before. So for all the protocols that I just talked about, they all fit within that 10 nanosecond constraint that we had. But we wanted to see if more complicated protocols could potentially also be implemented in Tonic or not. So what we did was that we basically generated these random programs that had different, so they had different length in their dependency chain. So if you took the longest dependency chain in the program logic, we tried to have like a wide range of those dependency chain lengths in our auto-generated programs. And we observed that, for programs that had about 31 levels of logical dependency, they all met timing. For ones that had more than 42, they kind of all consistently violated timing. For the ones that had between 31 to 42 logical levels in their longest dependency chain, depending on which operations were actually in that chain, they either met timing or not. And just as a just for a comparison, the 6 protocols that I talked about, they were all well within 12 to 29 basically logic levels. So the other thing we wanted to experiment with was how much user-defined state users can keep for each flow to implement their algorithms. And again, for comparison, those protocols that I just talked about used like 20 to maybe 50 bytes, but we can see that Tonic can basically support many more bytes than that for user-defined state, between 200 bytes and 400 bytes, depending on what credit management scheme is used. And in terms of window size, Tonic can keep track of 256 segments at a time, and assuming these segments can get large, like about 1,000 bytes, there's actually a lot of in-flight data that Tonic can keep track of. And in terms of number of concurrent flows, as in the height of the memory in Tonic, it can basically keep track of about 2,048 flows at the same time, which is comparable to other hardware offloads in the literature and in industry. And our final set of experiments were basically end-to-end simulations to basically show that Tonic-based implementations of protocols conform to their hard-coded implementation. So Tonic is basically not doing anything crazy, and things implemented in Tonic will have a similar behavior than things not implemented in Tonic. So what we did was that we basically developed this cycle-accurate hardware simulator for Tonic and then integrated it within NS3. And then we compared, we implemented, as I said, TCP Neutrino and DCQCN within Tonic, and then ran this end-to-end simulation and then compared the protocol behavior with their native implementations in NS3. So there's the plots that I'm showing here are for TCP Neutrino. The one on the left is a progression of congestion window for a single flow with random packet drops at the receiving NIC. And as you can see, Tonic and the hard-coded protocol, they both have very similar congestion window changes. And the plot on the right shows the sequence number that was transmitted outside of Tonic and the Tonic-based implementation and the hard-coded implementation over time. And the larger dots are the retransmissions. And as you can see, again, the behavior is very similar. So in terms of future work, what we've been thinking about, first of all, is to scale up to many more flows than 2,000 flows. And this can have applications in a lot of settings. If you have a lot of very short flows, so you don't have about 1,000 flows that need to have high throughput or low latency, but you have a large number of very short flows. And so far, as I mentioned before, the programmers need to write the programmable modules in Verilog. The API is still pretty simple, but it's still Verilog. So we've been looking at providing higher level programming interfaces for that. And also, as I mentioned before, all this discussion was on how to make the sender side of transport programmable. But since these receiver-driven protocols are starting to become more common in data centers and they're showing a lot of benefit, it is definitely an interesting future work to do to basically figure out how a programmable hardware receiver should look like. So to summarize, I presented Tonic today, which is a programmable hardware architecture for implementing transport protocols on high-speed NICs, and enables people to do that with modest development effort. And to do that, it basically exploits some domain-specific optimizations. We find common patterns across different transport protocols in terms of the way they select the next segment and the way they do congestion control and implement them as very efficient hardware modules. And that's it. Thank you for listening, and I'll be happy to take questions.
All right, so if you have a question, I think everyone's mics were muted by Jenna when you joined, but feel free to unmute, and if we have some crosstalk, we'll figure it out. So I have a quick one to get us going. Your previous future work slide had some ideas about maybe a higher level programming API. So wondering if you could say a bit more about what that might look like.
Sure. So something that we basically explored actually a little bit before this work was for congestion control algorithms and the way they adjust parameters. You can really represent a lot of them as state machines, and that is something that could be much more easier than writing Verilog code, and it can be transferred to a Verilog code very easily. So basically, just different states that your network is going to be. If there's congestion, there's a lot of congestion, there's no congestion, and what the rate is going to be, and what kind of updates you're going to do in every state. For segment selection, we haven't actually looked at it, thought about it that much, but I'm assuming you can do something similar because, again, you're keeping track of some state per segment. So I'm assuming you can basically have something similar, like a similar state machine for basically describing how you're going to move, change a segment's state from not sent out, transmitted, act, or lost, and then basically translate that to Verilog.
So maybe a non-technical question. I know that you've given some early talks on this work at various events, including our retreat last year. I'm curious if what kind of interest you've found in this work from folks in industry who are, building real cloud deployments.
Sure. People have been interested specifically in the programmable part of congestion control. I've both in the RDMA context and out of the RDMA context. There've been people from Xilinx who've showed some interest in the work, especially because I think people still have not been thinking much about segment selection, but congestion control is, so it can be so much customized based on what is going on in the network that, having it be programmable is starting to become very interesting to people. And in terms of the way this has raised interest in the RDMA context, someone from Alibaba mentioned this to me, is that, the current RDMA NICs have very simple loss detection and recovery mechanisms that is not very efficient over Ethernet. It is more efficient in infinite band networks. And again, that is something that would help people experiment with that. Another thing that I've heard from some industry folks is that, sometimes, especially if you want to offload, let's say you have like an FPGA on your NIC and you have some applications that you want to offload onto the NIC. And there's some applications that you don't, and you might want to use different congestion control algorithms based on the application to kind of take care of the applications that are on the NIC or they're not on the NIC. So like the different levels of applications that you might want to differentiate against based on where they're sitting, and basically having something programmable on the NIC that can help you with that would be useful in this context too.
So you mentioned that you implemented 6 representative transport protocols in Tonic, but
Right.
Do you have any insight on what are some other transport protocols which are not suitable for implementation in Tonic? Have you thought about that?
Yeah, that's a great question. So something that a lot of people have noticed, one of the protocols that we mentioned in the paper that we can't completely implement is Quick. And the reason there are multiple reasons. Most of these protocols have been designed to run in software, and in software you have, all sorts of resources. You can basically loop through an array multiple times. You can keep, a lot of state per segment. And Quick is one of those. Quick has some properties that are not really suitable for Tonic, and I believe for any hardware offload. One of them is that Quick keeps track of per packet timestamps, and it's just too many, let's say per segment timestamp, like for 200 segments, 32-bit timestamps, that's just too much state that won't physically fit. There is another thing there's something that really also helps us in Tonic in terms of offloading things to hardware is basically keeping track of packets kind of according to their sequence number. So if you just keep a continuous window and we can slide it forward, and although that is still difficult to do, it's easier because all the protocols basically depend on this continuous sequence number thing. But I think in Quick, there's sometimes you actually want to order packets based on the timestamps that they were sent or received, and that is again something that would get too complicated for Tonic to implement. So some of the things there's some workarounds around this. So for per packet timestamps, I think the reason Quick has per packet timestamps, one of the reasons at least, is to have very accurate RTT estimates. And one way you can get around that is to basically have only keep timestamps for a few packets out of the window instead of every single packet. But some of the stuff like ordering packets with something other than the sequence number is something that I don't think off the top of my head how it would actually be implemented in Tonic. So basically anything that is keeping too much state per segment. Like most of these protocols will just keep track of those few bits that I talked about, and then as the window moves forward, they kind of derive information about subsequent segments from those few segments. So, but anything that wants to keep a lot of information per segment would be difficult to do.
Last chance for webinar questions. All right, well, thank you all for attending. We'll be putting this video online fairly soon. And if you have further questions, Mina, I think you'll be at the retreat, correct, in New York City? Great, yep. So Mina will be at the retreat on October 11th in New York City. So you can follow up with in-person questions there. Thank you all again. We'll be announcing our next seminar in about a month.
Thanks. Bye.